The first system we're going to look at is a 440 watt 4-panel system. It uses 4 110 watt Shell 22 volt output panels. It has 4 6 volt 330 amp hour batteries configured in an array to give us 12 volts at 660 amp hours total. It has a 30 amp MPPT charge controller, one of the modern style ones. It has one 400 watt sine wave inverter and one 300 watt modified sine wave inverter that I like to call square wave inverters. First, we're going to talk about a 440 watt small system that you might want to put in, and it was put in this backyard with a lot of trees and a lot of sun blockage. So we had to look at a few things. First of all, we take a look up, and there's where the house and control box is, but the roof was no good because it just didn't have enough clearance to the sun. There was too much shading from trees. Using our protractor and looking at the angles, we could see that the tree line was high enough in the back that we'd actually have to raise the panels up and get them clear of the tree line so that we'd get at least 6 hours of sun a day. So in this case, the large pieces of pressure treated wood were buried several feet in the ground, and then when we got to the top, actually added 2x4s on both sides and bolted them through to extend it up even higher to get it raised up real high. Now, we've used this example of a panel install in other parts in the video, so you've seen the way this one's wired in the back. These are Shell 110 watt panels, and the boxes are wired in between them. You can see a grounding wire right in the middle there. And then some of this blue flexible conduit on the right was used to put the wires into and bring them down the pole like so. It comes all the way down, and then comes into a pull box right at the bottom over here. And this pull box is where we can disconnect the power. So at any time we want to, we can just pull out the T-bar in here and disconnect the panel array from the rest of the system. We felt that this one was so high that because that panel array acts sort of like a big wing, if real strong winds were to come, it might be a little bit of a problem. So we used guy wires coming down like this from the right and left, 4 points on the corners. These are actually high quality climbing ropes, nylon climbing ropes, which can be replaced every 3 or 4 years, and tied them down to the ground. And on the ground, we brought it down and put them in these small tie-offs, really just pressure treated 2x4s stuck into a block of concrete with an eyelet. You can see the eyelet over there, just tied off to the rope. For extra strength, a couple of diagonal pressure-treated 2x4s were added at the base just for extra strength. You really can't overdo it on any of these installations. It's just going to cost a little bit more materials. And those as well, pressure-treated stakes going right into blocks of concrete in the ground with bolts going through them. The feeder wire from the array is recycled off of an old radio tower. I picked it up in an old salvage place, really large diameter copper. And it really did work when we tested it with a voltmeter, and it's about to be trenched underground. In this case, the run up to the battery box was about 100 feet, so we had to run as high as voltage as we could up the cable so that we wouldn't have much loss when we got to the other end. To accomplish that, we had to run 2 of the panels in series and the other 2 in series and then parallel them. So we added up the voltage of 2 on the left, and we added up the voltage of the ones 2 on the right, and then we paralleled them so that we bumped up the voltage high enough we'd have less loss coming up the long run. Where the feeder cable comes in from the array to the battery box, we used a very inexpensive air conditioner pull box, and this allows me to just pull that T-bar at the top and disconnect the panels at this point from the rest of the battery box. Let's take a quick second to review the wiring of the pull boxes. And these are, number 1, as I'm showing, at the panel array. You have a pull box there. Or number 2, the box at the battery box. That's at the other end of the line of the wire coming from the array up to the battery box. So for number 1, your positives and negatives in and outs would be coming from the panel array output, positive on the far left, and then going out and going to the battery box pull box input. Now for 2, that would be for the output of the array pull box. That would be coming on the wire from the arrays, that positive going into the connection on the far left, and then output number 2, the red one plus, to the charge controller input breaker. So you can see I've got your connections. You can freeze this and sort of take a good look at it as to the input and output of the plus and minus on the pull boxes, either at the array, that would be number 1, or at the battery box, number 2. In this box, simple hinges are used on the lid over here. Of Quite straightforward. 4 of them across the back. I even recycled some old gas lifts off the back of a hatchback car and put them in here with bolts so that it could assist in lifting up the lid, which is a little bit heavy because of those comp shingles. Just use a piece of 2x4, put a bolt through it. Same thing on the bottom, just put a bolt through the box. The wires from the air conditioning pull box actually just have a hole drilled in the side of the box. Little strain reliefs around there with the ground wire going into the charge controller, mounted right in the back of the box. Now a lot of people say you should have the control box in a separate compartment. I do suggest that, unless in this case it's such a small system and the box is so well power ventilated that you don't have any gas buildup in there. And notice this little gizmo. It's just a piece of wood with a bolt going through the back, and it tips up like that to hold the lid open while you're working on things. Now remember how I showed when we were making battery boxes that we put those little lips of wood at the bottom, and that actually lets it sit on top of the slab. And then I used a little bit of PL400, that type of liquid nails adhesive, to sort of set the box on top of the concrete block, and a little bit of pookie, as they call it, a little more caulking and such, just caulking and gluing together. Gluing and screwing is always very strong. The batteries are wired together using these 2 wires and traditional kinds of battery terminal lugs like these you can get in any auto parts store. I doubled up on the wire because I just happened to have enough, and of course more wire means a lower resistance and a better connection. I tried to color code them when I had the right colors. Black and red, a little bit of white I used there. And then notice that what we've got here is 2 batteries in series to make 12 volts. These are 6-volt batteries in 2 pairs, just like the panels really. 2 in series, and then both of those 2 packs of 2 are paralleled. So on the bottom you can see that the wires are jumping between the positive terminals, coded red here, and then taking off, and the same on the other end with the black. Jumping from this one directly to that one, but that each 2 batteries are then in series positive to negative in the middle here with these 2 connections, giving us 12-volt system with the amp hourage adding up from the 2 sets. On this small system, I used a single 50 amp breaker coming out, was all I needed to feed the inverters I was feeding. No more than 50 amps I was ever going to draw, and put it into a small project case like that. A big piece of red tape on the top indicating up is on. So this is a way of enclosing one of these simple breakers, and then the wiring goes out the back of the box. There's our power output from the output breaker coming out, a PVC tube over this railroad tie wall, and then go ahead and bury it in the ground, and it goes back up to the house. Here's our control panel in-house for the 440 watt system, and I decided to put our 2 inverters here, our sine wave on the top and our square wave on the bottom, inside the house in this case, because on the smaller inverters they don't come with remote control switches on them. So to be able to access them and turn them on and off easily, I had to bring them in the house. I just had to use large enough wire to get to them and feed them power without having any loss coming in from the batteries. On the bottom right, I have the incoming power going into another one of the inexpensive air conditioning pull box where I can pull this T-bar at the top and disconnect the system. So it's good to have those type of things anywhere in the system so you can turn off the power. On the top right is the remote control head from the outside charge controller, and that is telling us what amps and voltage we have coming in at any given time. So we can see right now, looks like 14.6 volts charging those batteries at about 7.4 amps. Coming in. It also tells us what state of charge the battery's in as far as how they're being charged. In this case, we've got float, acceptance, and bulk charge, and then we have an equalizing charge depending on how it's flashing, how that green LED is flashing. On, off, on, off. It looks like it's the middle one in the acceptance mode. So the batteries are fairly well charged right now, and they're not, if they were fully charged, you'd see the top one, the float, and the LED would be going bink, 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 sort of fast. If it's just on, that means it's giving it full power. So right now, they're somewhere in the middle of their charge state. You see the 3 batteries there, low, sort of almost topped and then topped. So we might be getting more current into the system if the batteries were really dead. But since they're pretty much charged, we're not getting a heck of a lot of current. But if you multiply those voltage times the current, it would tell you how many watts are coming in from the panels. The reason it's sort of flashing is because of the video, not because that display is flashing. So there we go. We've got 2 inverters on this small system. The bottom left one over there is good for lighting. I drive a lot of high efficiency bulbs with that. And then the one on the top is used for the large screen TV and computer system where we do need that pure AC. And this is all mounted on a steel plate away from the wall over here. And the system is completely autonomous from the housing wiring system, so there's no connection to it whatsoever. Our second system is about a 2100 watt system using 12 panels. It has 12 180 watt panels putting out around 23 volts each. It uses 24 330 amp hour 6 volt batteries, and we have arrayed them for 1800 amp hours at 24 volts. It uses an 80 amp MPPT charge controller and one 4000 watt sine wave inverter. At this house, a 2.1 kilowatt solar power station was installed recently. We're just finishing it up. And his roof, although it was okay mechanically for mounting panels, was no good as far as getting them up and into the sun. Plus, we had two large trees across the street, right in the way of our south sun path. So we went with pole-mounted arrays with pre-manufactured array mounting frames. There's 12 180 watt panels that are grouped as 6 on each one of the pole mount frames. We ordered mounts from Zomeworks, a trusted old manufacturer of mounting frames, and they custom manufactured these exactly to our specifications for the type of panel that we were using. The panels were connected together by snapping their connectors together through the boxes and then dressing the cables down the frame and tying it off with tie wraps. You can see the mount on top of the pole, which comes with the frame, is a nice cap mount, and it has the bar for adjusting the angle according to your seasonal change in sun angle. Each 6 of the panels were combined in a small combiner box at the top of the pole and then run down in a PVC pipe straight down to the bottom and then trenched in on the left-hand array under the ground over to the right-hand array and combined in a small pole box at the base. The combiner box on top and this little pole box were attached to the pole by drilling holes directly in the pole and then using a tap to put 1/4-20 threads in and screwing them right onto the pole with a little dollop of silicone under it to seal it. You can see that the panels are mounted onto the frame with their hardware right there, and the holes are pre-drilled and exactly match the panel holes. And you can see that we left extra cable. We did not cut it off because there's going to be a certain amount of length to the connector on each one of these panels, and then dressed it off and tied it up with tie wraps. The 17-foot poles were put 1/3 into the ground. That's a good rule of thumb, 1/3 of the pole buried. And that's 1/4-inch thick steel Schedule 40 6-inch diameter pipe. Then we just framed up the top of the concrete with 2x4s and filled it in. As you can see, it's piped over to the other one underground. Our few trees across the street are going to be taken down, and that'll open up our sky and our view, especially in the winter when the sun angle is lower in the south. So those two will be dropped that way, away from the panels. The power trenched under the ground coming from the panels comes up in the PVC and goes back into the box back here. You can see our ground wire coming out on the other side and going down to a ground rod down here. Here's our main breaker box and our charge controller. Breaker box, charge controller, and our forced air blower. This is sucking air from underneath the house and blowing that temperature moderated air into the box and pressurizing first the electronics bay and then into the batteries. You see we have that separation panel there. That's optimum. We have especially in larger systems like this. What is convenient to do for your end users to label all the breakers with clear instructions as to what they do. Here's the whole system shutdown sequence, which breakers to turn off and on first. There's the marking in the breakers, up, down, on, off. So everything is very clear for the user. Then our main information display on this Outback MPPT controller is right here. You've seen this before. An important hit point is, since your charge controller is powered by the batteries, it always has to be turned on first and turned off last.
Always turn on the circuit breaker from the batteries to the charge controller and let it boot up before you turn on the circuit breaker from the photovoltaic array feeding electricity into the charge controller. The computer in that charge controller has to turn on and see the world first. Then you can turn on the photovoltaic array and feed energy into the charge controller. So let's take a look in this system and see how our wiring is routed in from the panels to the circuit breaker box, and then the charge controller and our batteries, how they're all tied together. So we start at the top left where we can see the red wire coming in. It's a little bit smaller than the larger wire to the right, but it is the power coming in from the solar panels. And it goes down and is hooked to one of the two 90-amp breakers. Down here, this is the disconnect breaker that turns power off coming in from the panels and also gives it some protection, being it's a circuit breaker. Then that incoming positive lead from the solar panel going through the circuit breaker comes out of the bottom of the circuit breaker box through that strain relief and goes in through the bottom of the charge controller box in through its strain relief. We've also brought the same diameter black colored wire as the ground from that grounding post inside of the circuit breaker box through the same strain reliefs also into the bottom of the charge controller. Looking at the wiring connections inside of the charge controller, the connections for PV input and batteries are clearly marked on the circuit board underneath the wires, so you really can't go wrong. We're going to attach the red and the black wires coming in from the solar panels to that breaker into our PV in connections on the circuit board of the charge controller and tighten them down, not too tight. Then we're going to take two pieces of the same gauge wire, red and black though, and go on the output. It'll say batteries connection, and we're going to take those back out the strain relief on the bottom. One of those wires is going to go over to the batteries and directly connect to those. It's the ground. And the other one is going to come back into the circuit breaker box to go through another circuit breaker, in this case a 90 amp, because we know we have an 80 amp charge controller. It will never put out more than 80, so we're putting in 90 in there. 100 would be fine. You need a little bit of elbow room, and it's going to go back through a safety breaker that turns off the power between the batteries and the charge controller. So the output of the charge controller goes through the small breaker and then comes back out the bottom of the strain relief and goes over to the batteries, and that completes the circuit of the output of the charge controller to the batteries. Now let's look at our big 175 amp breaker, and this is for the output of the power of the batteries going to our large inverter. It's quite a bit larger, and it's got a big throw lever on the right side of the box. And that is going to be the plus lead again. All the grounds are going to be to that common grounding point. But in this case, our large 2-gauge wire is going about 8 feet. It's going to go through this breaker, come from the batteries. The large one goes into the box from the batteries, goes through that breaker. That hot lead goes through the breaker. It comes out the other side of the breaker, and then is fed out the strain relief in the top of the box and goes out through our conduit pipe under the house and into our inverter. This gives us the protection we need as far as the circuit breaker for the output of the batteries to the inverter, and it allows us to turn off the power from the batteries going to the inverter. The only remaining wire is our bare copper wire, which is connected to one of the ground posts on the top left, either the bar that we put the wire through and tighten it down, or the one with the lugs. Take it out of the box assembly completely and put it to our ground rod on the side of the battery box. And that concludes all of the basic wiring paths that we're seeing in this control box in this installation.
Power is then fed out of the back of the battery box and underneath the house into the inverter, and then comes back out and through this standard AC breaker box where we feed each one of the circuits in the house. And what do we see here but our 4,000 watt sine wave inverter underneath the house? The wires coming in up here, and then going down to the inverter over here right on the side. And you can see that it has strain reliefs just like our other boxes and equipment. And this is the power going out. Our power coming in comes in 2 large wires. You can see our plus and minus from the battery bank comes into the back of the inverter, and the red cap is over the hot wire there, the plus wire, and then we've got the ground wire as well. And you can see it's blinking because it's in sleep mode right now, waiting for a load to come on, waiting for somebody to use some electricity. Everything is well marked on there. I've taken the hatch off of the side here where we can see the connections next. This particular model has two outputs on it. So we have a couple of pieces of Romex coming out of it, of this block. You push the wires in and then put your screwdriver in and screw them tight right into the hole there. And then we'll put our cover back on it here to keep it protected once we're finished wiring it up. And you can see where our wiring is coming in underneath the house here, that there's an intake with that dryer vent that I'm using to pull air from underneath the house here, which is going to be cooler in the summer and warmer in the winter. So it's sort of preconditioned, and that positively pressurizes the box outside. In this case, the 4,000 watt sine wave inverter is underneath the house, secured to a pile of 4 cinder blocks.
To reinforce what we've just seen, let's take a look at a block diagram of this system. On the top left, we see the photovoltaic array in purple, and it comes out and goes into the combiner box, then comes down the pole into that pole box on the bottom left, and then comes into our white circuit breaker box. That's the big box in the center. That purple line is the plus. All the blacks are common ground wires, which are all connected to the big lugs inside the white breaker box. But the purple line, which is the plus from the photovoltaic array, goes through circuit breaker 2 and over to the input of the charge controller. Then the output of the charge controller comes back, that red. See, the black line is common, that's ground. The red comes back to circuit breaker 3 and then comes out of the breaker box again and goes to the battery bank plus. The green on the battery bank is also the plus of the battery bank, and it goes through the large circuit breaker on the top right, and that's our master shutoff for the inverter. That plus then comes out of the other side of the circuit breaker and goes out to the inverter's plus input. Then on this system, we do have a separate outside breaker box, and that has 3 15-amp breakers in it, and the AC outputs from the inverter go to it, and then the outputs from it go to the outlets in the house. Now, what I'm going to say in the next 2 minutes is extremely important. It's priority 1, so take notes on this. The circuit breaker size determination. We've got 3 main breakers in there. Number 1, the photovoltaic array coming into the charge controller. We're going to put a breaker in there so we can turn it off and protect that circuit. Number 2, out of that charge controller, the output goes to the batteries to charge the batteries. That's where our number 2 breaker is going to go in. These are our 2 smaller breakers. They can go in the same housing, but they're both smaller breakers. And the number 3, the larger breaker between the batteries and the inverter. In other words, the battery bank's output going into that inverter. It's going to be a larger breaker. Number 1 needs to be 1.5 times the maximum output of the panels in amps, around 1.5. Those panels can actually put more power out instantaneously because of a little bit of a lensing effect. When the sun comes out behind clouds, there'll be an increased power, so you do need a little bit of elbow room there. 1.5 is a good place to be around that level. Number 2, the charge controller output to the batteries for charging, 1.25 to 1.5 times the maximum output of the charge controller. I'm going to show you how to calculate these. You can go a little bit less on this one because it's not going to swing quite as much. And then number 3, the large one, 1.5 times the maximum inverter current draw that you can ever expect. Now let's take a look at how we calculate these. The first thing I want to say is these circuit breakers must be DC type, not regular breakers you get from a home improvement center or electrical contractor center. You'll need to order them special from a solar supply house. They're going to cost a little bit more, but you must use this type. So in number 1, our panel's output into the charge controller. We're going to put a circuit breaker there. And what you do is take the array's total wattage, you know the total wattage, maybe a half kilowatt, kilowatt, 2 kilowatts, and divide it by the voltage output. That's the configuration, the way you've put those panels together to run that higher voltage coming in, or maybe it's whatever the voltage is. Divide that voltage into the total wattage of the panel, and that's going to be the maximum amount of current that you're going to see coming from this array. And then we're going to go with 1.5 times whatever that amperage is for that safety elbow room. Number 2, the charge controller's output, going from the output of the charge controller into the batteries to charge the batteries. We're going to put a breaker there, and that is the array's maximum wattage divided by the battery bank voltage. That's going to give us the maximum current that that charge controller is going to ever deliver to the batteries. And like I say, it's a little bit safer to run a little bit less of a circuit breaker there, capacity if you need to. 1.5 is ideal. You can come down a little bit. The output of the charge controller is protected inside the circuit itself, so you get a little bit of extra protection there to begin with. And then the big one, number 3, the battery bank's output going to the inverter input. That's where our big load circuit breaker goes that provides power to the rest of the house and everything else. So that's the inverter's maximum wattage, whatever that is, divided by the battery bank voltage. And that's going to give the maximum amount of current draw. Of course, it's not 100% efficient, so it may draw a little bit more than that, but that's why we give it the elbow room. Plus, all of these inverters have a little bit of surge capacity, so momentarily, instantaneously, a larger amount of current may be drawn. That's why it needs the full 1.5 amount, and you may can go a hair over that, and these large breakers tend to come in 150, 175 amp size. Again, all these 3 breakers can go into the same box. They're just going to be wired separately. What we're doing here, take a look. We're using the old formula, watts, volts, and amps. If you divide watts by either volts or amps, you get the other one. So watts divided by volts equals amps, and watts divided by amps equals volts. Whichever one you don't know, it gets that one for you. Now, breakers don't come in every size imaginable, so take the number you come out with and round it up to the next size breaker that is available. The third system we're going to look at is a 2880 watt system utilizing 48 panels. It has 48 smaller 60 watt panels at about 18 volts each and utilizes 4 12 panel arrays with automatic tracking. It has 12 1700 amp hour 2 volt batteries, large solar design batteries for a total of 1700 amp hours at 24 volts. That's the battery bank design voltage. And it uses an 80 amp pulse width modulated charge controller. It's not the new MPPT style, but it's a good one. It has one 4000 watt sine wave inverter. As you can see, 12 panels are mounted on each frame, and they're on individual steel poles mounted in cement. They're connected together with a wire race, and they utilize a gas-based automatic tracking system. The tracking system utilizes gas-filled shock absorbers and Freon gas, which actually positions the panels automatically without the addition of any external power. In this case, tubular concrete forms were put into the ground and then backfilled with concrete with the steel poles in the center of them. As you can see, a combiner box was used to take the outputs of each set of 3 and parallel connect them to add up the amp hours inside of the combiner box. Then, just plus and minus comes out with the black cable. This installation utilizes a small separate building for the equipment and the batteries, and it has it cut into 2 rooms. This equipment room looks more complex because this system has a bunch of extra features built in, like AC grid-powered battery chargers, so you can charge the entire battery bank from the commercial mains if you wanted to. It has a 5,000 watt gasoline generator as a backup. It also has dual charge controller remote display for in the house and in the equipment room. He also has a solar water distiller right out back for battery water, making his own battery water. And it also has independent array shutoff and fusing. Each one of the arrays on the poles can independently be turned on and off and has its own fuse. Plus, you're going to see some shunts up on the panel for sampling system conditions. If we take a look at this very full-featured system, on the top left he's got the 4 panel arrays coming in with separate wiring to 4 switches and fuses. Each one can be turned on and off so that you can isolate one panel array from the others. Then it comes down and goes right into the charge controller. After that, out of the charge controller, it goes through some fuses. Of course, circuit breakers or fuses are used here, but he's using fuses. And then into a central switch. That's the big battery switch, the red switch. And that battery bank is connected to that switch along with a charger which will be charging the battery bank, and as well an AC mains charger bank, so he can charge his battery bank off of a plug-in AC mains grid chargers. Those are the 4 silver ones on top. The battery bank, of course, also goes through the switch to the inverter. That's a big, nice 4,000 watt sine wave inverter with its own LCD display on it. It comes out and goes through a traditional AC circuit breaker box which feeds the home. But at that point, he has a 5,000 watt generator which can also be actually mechanically connected to that circuit breaker box and then feed the home directly from the gasoline generator. And here's where the panels come in, to 4 fused switches. Now this system again is about 15 years old, so switches and fuses were used. As well, circuit breakers could have been used in this position. Just 4 DC breakers in a box, each one being fed by a different panel array. So you can duplicate this for as many panel arrays as you have, or you don't have to separate them. But it gives a little bit more flexibility in case you wanted to take one of them down and take it offline to work on it. And here's the charge controller. It's a PWM, or what we call pulse width modulated charging controller, and that uses the 3-stage charging that we've talked about, so it does a very efficient job of charging the batteries, but it is not an MPPT type of charge controller, so you don't get that extra 30% boost. Notice he's keeping a paper log attached to the charge controller of daily performance. The output of the charge controller goes through 2 cartridge fuses under these plastic protective covers. In this system, a large switch with an embedded fuse is used to connect and disconnect the main battery bank. Of course, instead of a box, we have an actual building, so this equipment, our charge controller and inverter and switches, are mounted right on the wall on insulating surfaces. You can see on the bottom left the big red switch with the fuse inside coming from the batteries. It's got, of course, the very large wire coming in from the batteries because they're going to go to the inverter. And that it comes up to 2 buses on the right. These are the bronze one on the bottom, the negative connections, and the one on the top, the silver colored, is for the positive connections. You can see that the wires on top are either red or marked with red tape. Now, the ground bus on the bottom looks a little bit more complex because it has shunts hooked onto it, and these are used for sampling off information to go to the displays. You can see the fuses on the top left coming from the charge controller, and you can see the 2 large wires on the right going off to the inverter input. The inverter is a 4,000 watt sine wave unit. You can see the large diameter wires feeding in over the top, and it has a nice integrated LCD information display. The output of the inverter simply feeds traditional AC breaker boxes feeding to the house service outlets. Although I feel it's sort of redundant, a 5,000 watt gasoline generator with a starter battery with its own solar panel is ready to go and plug right into those service boxes to feed the house. The battery bank is a 24 volt system built with 12 2-volt 1700 amp hour Rolls-Charette solar design batteries. These are really the top shelf that you can get in industrial batteries specifically designed for solar applications. As you can see, each one is wired to the next, negative to positive, to form a series battery bank at 24 volts. Extra flexible double-aught cable is connected to each one of the posts using traditional hardware, and then non-ox compound has been put over the connection to keep it from oxidizing. And as a bonus, there are 24-volt battery chargers plugged into the AC commercial mains, ready to charge the entire battery bank up should the sun unexpectedly go out. Don't be intimidated by the complexity of this system, because much of what was done here was over and above what was needed to reliably and safely produce the power. System 4 is a very typical smaller system, and it's interesting to see. It's an 800 watt total system using 4 200 watt panels. Those are wired in 2 parallel sets of 2 panels in series. So 2 in series, 2 in series, and then paralleling those on a 24 volt battery system is being used with the large 8D sized sealed batteries. We're using a FlexMax MPPT 60 amp charge controller and a 1500 watt Go Power sine wave inverter. Let's take a look. Here's an 800 watt system using 4 200 watt panels. They've been split into 2 arrays over here because it gets a little unwieldy with too much weight, say if you had 4 panels on one frame. Wiring is identical on both of these 2 set arrays, and that flexible blue conduit makes it really easy to run the wire down and parallel both of these arrays in the box at the base. The outputs from both of the panel arrays were combined in a combiner box at the very bottom, and then the output of that is run into the ground for the underground run up to the battery box. Angle adjustments are made quite easily using the angle bars there and the little metal axles that go right through the wooden struts. The feeder cable from the panels up to the box
is a recycled radio station coax off of a tower. Inexpensive, very large. And there's the outside pull box mounted on the battery box. Typical air conditioner pull box. There's that outside pull box, the outputs of which come right through the wall of the battery box, go along the inside, are tacked to the wall, and then go into a circuit breaker box. This, of course, is the input breaker coming in from the panels. And this was made with a little plastic project box and cut out with an X-Acto blade so that the circuit breakers fit right in there and screwed right in the top. Not bad, eh? So there we go, the number one breaker being the panels coming in, and the number two being the output of the charge controller coming back out and going to the batteries. So we house those two smaller breakers in there. Now, you'll see that these 8D forklift batteries are stacked tightly on top of each other and wired with nice short runs of wire. And our inverter and charge controller sit nicely on top of two wooden planks that fit on the top. This is the Outback 60, FlexMax 60. And we have the standard arrangement here of wiring that you've seen a million times in this video already. But in the cooler environment where you can do this and you have very good ventilation in the box, you do not want to do this with batteries which are outgassing heavily and you don't have good ventilation. So with good ventilation in the box, this inverter and charge controller are in here, and the output of the batteries goes to the large breaker. Here's a 100 amp breaker in this case for this size inverter, and it's stuck right in a little project box and right onto the side of the inverter. I'm just using double sticky tape there. You can see the output of that breaker going right into the back, into the input of this inverter. And then the output of the inverter, which in this case happens to be an outlet, an actual outlet, a GFI outlet. Sometimes they're not, they're just bare wires. It's going out. And we'll show you how we wired it into the house.
Now, ideally, for safety, the charge controller and the inverter should be in a separate compartment that's isolated from the air that ventilates the batteries and the gases that come out of them.
Inverter AC actually goes into a piece of PVC which is buried underneath the dirt over here, pops up over this little railroad tie wall using the PVC, and then is buried under the bushes. And let's go up to where we buried it all the way to the house here and took advantage of something that's really convenient. It is an outdoor outlet. Now, this outdoor outlet had another hole in the side, a punch out you could punch out, so I put the PVC right into it and I wired it through the wall into the house. And we'll show you how we dealt with that in the house. I mounted a metal 4-outlet box inside of the house, and the 2 outlets on the right are solar. The 2 outlets on the left are the existing wiring that was in the wall. It's actually just feeding along as it usually was, but I have the other wires coming in from the solar AC outlet coming right through the wall, and they're feeding the outlets on the right. What's really keen is I ran an extra set of 2 wires coming in from that inverter, and I soldered them across the on switch. The on switch is just a connection of 2 wires together, and I brought it in here to a small switch on top of the outlet. So all I do is, if I want to power it up, I throw the switch and wait about 8 seconds, and the inverter boots up and power comes out of the outlet. There we go.
So we took a look at 4 different configurations and sizes of systems. Now, yours may be similar to one of them, so use the aspects of that system which work in your system and then customize the things which don't.